Hi everyone, we've come to our last lecture on Markov chains. We're going to prove the brute force method for calculating our representative quantity in the hidden Markov models. And then we're going to see a cheaper method, much cheaper method called the hidden Markov model forward algorithm. And we'll compare the costs a little bit carefully. And then we'll prove why this other algorithm also works. All right, let's get going. So we'll start off by proving the proposition that we saw at the end of the last lecture for a certain quantity associated with a hidden Markov model. And we called this one, we're going to see a couple of ways to compute it, but this first way that we're going to prove that we had a proposition for last time was called the so-called brute force method. So just first of all, just recall what that was. So recall from last time. This is the so-called brute force proposition. And we're trying to compute a sequence. So remember, the hidden Markov model has these two processes. There's the process that we called X and the process we called S. The process we called X is the so-called observed one, or the state-dependent process. And that one could be either continuous or discrete. And so we'll use our notation that we introduced last time for that satisfies that can be either. And so we want to make a prediction for a sequence of values over time that thing takes on. So the state dependent or the observed process. So we'll say there's capital T different values that we want to make a prediction for, a calculation for, either for its probability or its probability density, depending on what kind of a process it was. And so the formula that we wrote a proposition for last time, it's a bit long, but it really only has three main pieces. So we'll write it out. So we've got a series of sums at the beginning for each of the different time steps of the hidden process, taking on each of the different possible values that the hidden process can take on. So this is an n state, capital N state hidden process. And then there'd be another sum, S2 equaling 1 up to capital N, and so on. And then this finishes with S capital T equaling 1 up to capital N. So a whole bunch of sums there. And then we have a probability for the first value, or the initial value of the hidden process. So that's the state vector. We'll talk about that in a second. And then we have a pair of products. So we have product over all the different time steps. So we'll say A equaling 1 to T of this probability here, or density, depends on what it is. So F of state-dependent value given hidden value. And then another product here, starting at 2. Sorry, this should be B. B equals 2 up to T of a one-step transition. So say S sub B given S sub B minus 1. This is why it starts at 2. Okay, so it is a bit long, this expression, but if you think about it, there's only really three parts on the right-hand side, right? So there's this guy here, these guys, and these guys. Of course, there's lots of those individual things, but there's three kind of types of things. So let's just remind ourselves, these are the things that we need to know. F of S1, this thing is what we called before, like the components of our initial state distribution. All right, so we used to call that time 0. We'll call it 1 now. So that should look kind of familiar. And another quantity, the next one that shows up down the line is F of x sub a given s sub a. And so these are the state-dependent probabilities, or the distribution of the observations. So these are new. You can have lots of different words for this, but I mean, it's straightforward what it is. And then the other thing that's not new, that's present here, is the last item, s sub b given s sub b minus 1. And these guys, in our previous work, we were calling these things like Pij. I'm putting tildes here because these aren't exact, like there's no j on the left-hand side, there's no I on the left-hand side. These are the quantities you're supposed to think of from previous work. All right, so this is like a one-step transition probability matrix. This one is the initial distribution vector or state vector. And this guy is just new, right? There's two different processes. One, it's the probability of one process given the other. So that's a new thing for us. We'll have to work with that one. All right, so we can prove this now. It's not an elaborate proof. But there's enough symbols flying around that it's probably a good idea to kind of take it a little slow. Make sure you understand each of the different steps. So I'm going to do that maybe a little slower than is necessary. But so let's start with the left-hand side. And we're just going to use the total probability theorem, but we'll do it like sort of, you could just do it in one fell swoop, but I'm just going to do it a little slowly. So say I'm going to expand this over all of the different values that the hidden process can take at time 1. So this is time 1 value of the state. And so it could take on n different possible values. And each of those collectively, those values cover up the entire state space for the hidden Markov chain. So here's the x's. And then we'll just put on here add and s1. But we're just summing over all of these and covering up that whole state space, right? So we're just basically doing the total probability theorem, but doing it a little slowly. All right, and so the next thing we would do is just repeat this for all of the different time steps. So we just did it for step 1, we'd do it for all the other ones. And so I'll kind of duplicate this. And so we're going to have more times. So we'll have like the sum over S2 equaling 1 to n up to the sum over S capital T equaling 1 to capital N. And so S2 up to ST. Right, so that's the first step in this process. And now we just use the definition of conditional probabilities to kind of simplify this. And so I'm going to do a lot of duplication since there's so many repeated long things here. Right, so this joint probability could be written, how am I going to write it? Am I going to have room here? Let's see. So I want to write it using here, this is what I want to write. Like that, right? So that's just using the definition of conditional probability. So you could have just made all these lines in one step, I think. That probably would have been fine for most of you. Now we're going to focus on each of the different pieces here. So let's look at the first thing. I want to look at this guy here, right? And just remember, so recall, you may have to look back at the last lecture, one of the rules for hidden Markov models. So it's one of the properties in the definition that this joint distribution can be written as a product of a bunch of simpler joint densities or probabilities. And so we'll just write this here. So this quantity here could be just written like this. A product for A equaling, so over each of the different time steps. Like that, right? So that's one of the rules in the definition of the hidden Markov model, right? So that's the first thing. The next thing now, focus on the last term. Right, so let's go grab it. This guy here. Now, this guy, the first thing I'm going to do is just rewrite it using conditional probabilities again. I go up to t minus 1 here. So how do you say this is like conditioning on? Well, you can say it in lots of different ways. Okay, so that's just using, again, the rules for conditional probabilities. Or the definition, rather. And then we use the Markovian process that says that this first thing we can, or sorry, this last thing here, this guy is the same as the conditional probability with just this one, right? So that's the Markovian property of the Markov process or Markov chain. Sorry, I think I said that wrong. It depends only on the most recent one, which I wrote as being way over here, not this one here. Just like that. Okay, and then you just repeat this. So keep on doing this. So repeat. Until you got only one term. Until you get the following thing. So we get this one starts out at 2 because of the way we have time starting at 1, and we're going to write this index like this. Like that. And then if you combine, so which 3 things do we have here? So we've got, if you substitute this guy in for here, and then you substitute this guy in for here, you get the expected form. So I'll leave that substitution to you. So remember, this method of doing things was pretty expensive. So brute force, the cost in terms of like operations, like multiplications and stuff like that, is something like t squared n to the capital T, which can blow up pretty fast. If you do really simple systems like n equals 2 and t equals 3, like the kind of thing you would see on a homework or something like that, then it's totally manageable. It's not really manageable to do by hand, really, but you could do it on a computer pretty easily. But if you increase the number of times, this thing goes up pretty fast. So you can kind of see, I think, the fact that there's n to the t there is big. And so you can kind of see that it's a costly thing. And so there's a better way. And the better way we're going to introduce using a new quantity that we'll call the forward probability vector. So better way, better, cheaper way. Use what's called the forward probability vector. All right, so we'll just define that here. All right, and it looks like this. So we'll call it alpha sub j, or sorry, alpha sub t. And then it gets an argument of j, right? And it looks like this. So we'll have to kind of explain it a little bit in our notation. So we've got f and then a sequence of x's. So the whole time sequence of x's there. And then one value at time t, sorry, this was supposed to end at little t, of the Markov chain. And this is equal to j, right? And so this is, just remember, this thing is the same. So let's write this over here. So this is the same as capital S sub t is equal to little j, right? But we're just using this notation where we indicate these things with the lowercase value. It's getting a little bit overloaded, I would say. But so this is the jth component of this vector, of the forward probability vector. So you could write it as alpha. And so we'll write it as a row vector. Like that. So it has n components altogether if the Markov chain has n states. So let's take a look at that cheaper way to calculate things. So we'll write it as a proposition, of course, and we'll name this one the hidden Markov model forward algorithm. All right. And so it's written in terms of these forward probability vectors. And so here's the proposition. So we say that alpha 1, the whole vector, looks like this. So it's the initial state or distribution vector times this matrix capital omega. And that depends on x1. And we'll say what that is in a second. And then alpha at other times, so we'll say alpha t plus 1 is equal to alpha at the previous t times p, where p is going to be the one-step transition probability matrix for the Markov chain, and then times this same omega matrix evaluated at x t plus 1. Right, so this is the claim for how these how you get these different forward probability vectors. So just as a reminder, so here u1, right? This thing is just a vector. Looks like this, like u1, 1 up to un. One for each state, one for each value that the Markov chain can take. And each of these guys, ui at time 1, say, or sorry, not, yeah, is the probability that s sub 1 is equal to I. All right, so that's just the initial distribution vector. And then P is the usual. Right, so it's a matrix of Pij's. and each of these Pij's, this is the probability that Si is equal to, sorry, this is the probability that S2 is equal to J, given that S1 is equal to I. All right, and then there's that matrix that I said I would define, and so it looks like this. The matrix omega, and then let's say it's evaluated at some time x sub t, little t. It's a diagonal matrix. And along its diagonal are things like this. And then, so this thing repeats over and over again. Like that. All right, so here's the proof. There's really kind of two pieces here, right? We're trying to prove this line and this line. And the first one is really easy to do, so let's just look at that one first. So I'll just say clearly alpha 1 as a vector is equal to u1 times omega evaluated at x sub 1. And let's just see why that's the case. So you just write it out. Well, it's easiest to write this in sort of index notation. So we'll do that. So see what this looks like in index notation. So we'll say alpha 1, its jth component, right? And so what is this equal to? So this is uj 1 times, omega jj at x1. Or maybe you want to say omega of x1 at jj. Maybe that's a better way. Let's write it that way. Like that. All right, so clearly this is true if you just write out what these different pieces are. So alpha 1j, that's the same thing as f of x1 given s1 is equal to j. All right, so that's what alpha 1j is. And then u sub j at time 1, that's f of s1 is equal to j. And then omega at index jj, that looks like this. So it's f x1 given s1 is equal to j. And I think you can just see this is clearly true from the definition of conditional probabilities. The t+1 case is a little harder. For alpha t+1, we're going to go back to the earlier state here, earlier proof we were working on, and we're going to take this quantity here for two different values of t, and then look at what happens. Compare the two, right? So first, before we do, so just look at, so this quantity here is written as the product of these guys, and we had values for those. So here's the value for the conditional probability. It's this product, and the other one, the joint probability, is this other product here. And so we're gonna rewrite this stuff down here. right? Just borrowing from that proof. So you might need to reference back, looking back at that. But so here what we've got is the following thing. So x1 up to xt. So we're going to do this up to little t, and then the next one will go up to little t plus 1. So s1 up to s little t. Right, so this guy from the previous proof, and again, you have to look back there and remind yourself maybe. So it looks like this, f of s1, and then the product of a equals 1 to little t of f of xa given little s, given sa, and then times this other product, b equals 2 up to little t, and we have the transition probability matrix. Like that. Right, so that's how that looks for going up to t. And if you compare that to what does it look like when you go to t plus 1, and ask yourself, like, which things actually change, right? So what changes? So on the right-hand side, these things become t plus 1. So this is all that really changes on the right-hand side. So we get 2 extra terms in the product, and this is kind of the point. This is what we want to kind of notice. And then on the left-hand side, we've got t plus 1. Like that, right? And so what this tells you is that this quantity here is equal to the one before, but with the multiplying by these 2 extra terms. Right, and so times these 2 extra guys. Oops. Like that. Okay. And now we're going to sum over all the different values of s for some of these s's. All right, so we've got all these s's that we don't really care about actually. And so we're going to sum up until right before this to t minus 1, right? So let me write this out in words. So sum over all n values for s1 up to st minus 1. Right, so if you do that, all we end up doing is we just eliminate these guys and then up to t minus 1. So when we do this, we lose a bunch of the s's, so we get the following. And then these last 2 guys are the same. Like that. Okay, I'm going to rearrange these guys so that it'll look like the kind of expected result. Because maybe you can see it already. So this thing here, this is alpha sub t, s sub t. This is an element of the P matrix, so I'll just put like in quotes P. Right, that's the one-step transition probability matrix. And this guy is an element of the omega matrix. So what we're trying to do is we're trying to build this up into the sort of matrix equation form. So now if you sum over s sub t, right, then the left-hand side just loses its s sub t. And it becomes alpha sub t plus 1. Right? Evaluated at s of t plus 1. Right? And then the right-hand side, so sum over I equals 1 to capital N. I'm just writing out the sum. Right, so this is alpha sub t, its ith element. Right, that's just this guy here. And the next one is the same. And then this guy is the same. Now if we just rename, so now rename s sub t plus 1 to be j, right, then what we have here is alpha t plus 1 with argument j is equal to, and so we'll just copy this over, and then we'll put in the correct form for these two guys in terms of p and omega. So this first one here, this is going to be p, and this index is I, and this index is j, or sorry, this index is j, and this index is I, and so this is pij, and then this guy over here, this is omega at this index value, which is j. So to see that this has the correct, well, first, to see if this has the correct form, we should probably first write this thing in its complete. So put under here x of t plus 1. Right, now think about this quantity here. Right, so that is row I, column j of this matrix product. And you can see that from the, so let's write out matrix multiplication here. Let's say you have an index R, and then you've got P I R times omega R J. But remember, this omega is diagonal. Right, so this thing has the right form. And for what I've just, so this thing is in fact this guy here. And so then we've got a vector, its ith component, multiplying row I, column j of this matrix. And so what we have is the expected form. So we've got alpha t plus 1 is equal to the vector alpha sub t times the matrix P times the matrix omega at x t plus 1. All right, now as a corollary, we get to the thing that we were actually trying to use this for. Right, so we increment, we sort of ratchet up the time unit. So here's the statement of the corollary, and we'll just show it. F of x1 up to xt. This thing can be written by repeatedly applying the rule above and you get U1, and then a bunch of products of matrices. So omega at x1 times p times omega x2 times p times omega x3, and so on, up until p times omega of xt, and then multiplying by a column vector of ones. Right, so that is 1 is equal, well, 1 transpose looks like this. Okay, so that's the goal that we want to be able to compute, right? This thing that we want to have a faster way to compute. But look at the computational cost before we do the proof. Right? So each one of these, so let's look at these different pieces. Each one of these omega times p's, or if you want p times omega, right? Each one of these guys is n squared operations. Right, because there's n, it's a regular matrix in principle times a diagonal matrix. We just went through how the calculation works here. So there's n squared different elements you get there, and so you get n squared for each of these guys, and there are t of them. So n squared times t, and then I guess there's these two things on the end as well, which are also n squared. So let's just say plus 2n squared. So n squared times t plus 2. This is much, much cheaper than the brute force method. Okay, we can now go ahead and do the proof, and that'll be our last little activity of the class. All right, this is a straightforward proof. It's just a corollary here. So the first thing we're going to do is write the left-hand side. So it's just basically a direct application of the proof above. Right, so this thing is a sum over I equals 1 to n of all the different forward vector components. So x1 up to xt, and then s capital T is equal to I. Right, and so this is just a sum I equaling 1 to n of alpha t, its ith component. But that's just you could re-express that. So this is just a simple way to re-express that with a vector of ones, a dot product of this row vector with a column vector of ones. Okay, so that's the first part. And then for the next part, we just want to ratchet up, right? So we just have to figure out how do you write down alpha sub capital T. And so for that, we just build things up. So alpha 1, it looks like this, right? So this is part of the previous proposition. So that's U1 times omega at x1. And then alpha 2, well, that's equal to alpha 1 times p times omega at x2. And so that's u1 omega x1 times p times, sorry, I got ahead of myself, p omega at x2. Right, and so we just keep building this up. So alpha 3 is alpha 2 times p times omega at x3. And if you substitute in the previous line, you get u1 omega x1 p omega x2 times p omega x3. And so you just keep doing this, right? And you get alpha t is equal to u1. Then we've got omega x1 p omega x2 up to p omega xt. And that's alpha sub t, right? And so this gives us the expected result, f of x1 up to xt is equal to all this stuff times the vector of 1s. And that finishes the proof, and it also finishes the class. All right, everybody, that was the last of our Markov Chains lectures. We got just a little bit of a taste of what hidden Markov models can do, and I hope it interests you, and that maybe you look a little bit further and dig into the readings to see what more can be done. For any of the other topics that we might have covered, that you might do the same. You know, there's lots more information about these topics. For most of them, we just kind of gave a sort of a rough overview to get you comfortable and able to do some of the calculations. All right, thanks for watching. Bye.